Hi everyone, welcome to the Fast Mode Podcasts. Joining us today is Steve Douglas, Head of Market Strategy at Spirent, who will be running through some of the key highlights from Spirent's latest report, Cutting Through the Edge Computing Hype, MEC Latency Expectations versus Reality. So to start, perhaps Steve, you can bring us through the findings of the report, some of the interesting trends that you see in the MEC space.
Hi, Tara again. So let me give you first a high-level intro to the report itself, what the report was about. So it really, Tara, it came about fundamentally we were working with one of our customers in North America who'd asked us to benchmark their public edge deployments that they were doing with some of the cloud providers. They wanted to really get a better understanding, was it really delivering on the lower levels of latency? So what we came away from that there was, wouldn't it be interesting to actually do a global sort of benchmarking study independently of any customer, but also ask the demand side enterprises, would they be willing to pay for a lower latency type of SLA? So we commissioned, first of all, STL Partners, the analyst company here in the UK, to do a survey with 150 enterprises in North America, primarily in the manufacturing space, really to find out what type of low latency they would require from a 5G network for their applications, and also to understand would they pay to have that there guaranteed as an SLA. And then the second thing we obviously did was then we wanted to prove out, what actually latency is possible to be delivered in the real world from both the public cloud at a regional endpoint and the public cloud used as an edge in a city or a zone location. So that was the sort of the idea behind it. And the driver for this here was because a number of our customers were looking at primarily this here, Tara. They were looking at all of these potential new use cases they could monetize that were all requiring different types of lower latency. And what they really wanted to understand was, number one, could they meet those latency requirements? And then number two, how realistic are these latency requirements? Is this really what the industry actually needs? Because most of these numbers have come from, a mixture of different standards bodies, and it's not clear in the industry what really is needed out in the field, what a real end user actually needs. So the key for them was really around this here, Tara. Today, there's lots of issues on the end-to-end network which can impact the delivery of latency. Even with 5G today, you've got the air interface, you've got going through your core network, you've got the underlying transport infrastructure. All of those could impact latency. So the question they were looking at was, well, what if I collapsed the network down to the edge? So I moved from the sort of the top diagram here down to one of the options below, where I either bring in essence, the internet, the cloud, down to my peering points, basically at a city location, or I even bring it even deeper into the network, maybe even at a radio aggregation point, so it's as close to the end user as possible. Would that negate all of the potential areas in my network which would hurt latency, except for the air interface, obviously? So that was sort of the ambition that they were looking at. And then the question that we were asked was, okay, well, do we need to build our own edge, or could we actually use the public edge and the public cloud infrastructure to do this? Because all of the public cloud providers now have an offering which ranges, as you can see on the left there, from a regional type of deployment right down even to an on-prem deployment, which could be used as a private network. So that was sort of the idea for the independent sort of benchmarking. Let's go and test in the public cloud being used as an edge location versus just being used as a regional type of deployment. So the first thing was the enterprise survey, which is in the report, Tara. So this really was to ask this question: would enterprises be willing to pay, and what type of latency would they need? And I think the key takeaway here was on the left-hand side. Over 56% of those interviewed said they would be willing to pay, but the nuance here was that it wasn't just about needing low latency, they needed a guaranteed latency window. So they weren't looking for just one single number, they needed basically a window or a range that latency would consistently and always stay within. because if it fluctuated outside of those boundaries, that would actually impact many of their mission critical applications, which would be dependent on it. So it wasn't really about just making it low, it was all about the consistency of that their window. And when we asked them about what size of latency then would they need for their applications, this is where it got really interesting. There was a range of answers here. And I think the first key takeaway was that in most cases, the latency doesn't need to be actually that low for many of their initial use cases. So the biggest percentage there was asking for 20 to 50 milliseconds latency guaranteed as a range, while the second biggest was looking at 10 to 20 milliseconds. So that sort of is telling us, I mean, at this stage, we don't necessarily need the ultra low latency. You know, a range between say 10 to 50 milliseconds would be probably good enough for many of the use cases that, in this case, a big manufacturing industries we're looking at. Now, the second sort of takeaway here, Tara, which we find interesting, when we asked them for evidence of, you know, why do they think they need that 20 to 50 or that 10 to 20 milliseconds, they found it exceptionally difficult to give us a real factual set of evidence why they thought they needed that. In many cases, they thought that's maybe what an application developer told them. They believed they needed it. So they didn't actually have a true evidence as that is exactly what they needed. And actually, they came away saying, we probably would need to test that to figure out exactly what latency we would need to ask a service provider for, because this is just best guess in many cases from us. So we thought that was quite an interesting sort of takeaway from it.
Yeah,
So
Steve, if I may, interfere there. There's just one thing that I wanted to ask was that, we have these results, right? The 56%, looking at the 50 milliseconds or less. So if we were to go out and measure the network performance today, what would we see? What can we expect? Do you think that, when these customers come in and put these expectations, they have in mind that mobile operators would be able to cater for that? Or is that something that they know it's not in place right now, but it is something that they want to see happening in maybe 12 months down the road?
no, so this is and again, this is something we highlight in the report. There's a disconnect between what the enterprise understands, say 5G can deliver, and what's really available in the market. So in most cases, when we asked them, they understood that 4G technology couldn't provide the latency that they needed, or at least that's what they believed. When we asked them about 5G, they automatically thought 5G could already provide less than 10 milliseconds latency, because they had sort of read all the, I suppose, the marketing, or they had looked even at the 3GPP standards. And in many cases, this was an issue. They looked at the standards and then they saw that, release 16 and now release 17 are completed. So their assumption was that those would be available in the market. So they didn't understand that actually, no network in the world has release 16 deployed. There's no even devices or chipsets yet commercially out in the market. So everything is still release 15, which is running latencies anywhere between sort of 20 and 70 milliseconds in most commercial deployments. So they didn't understand that. And that was something they needed to be educated on, between understanding what, say, the 3GPP standards are promising compared to what actually is available commercially out in the real world. And there's certainly a disconnected there, Tara.
All right, excellent. So yeah, you were explaining, the highlights, right? So yeah, we can go back to the highlights, I guess, the
Yeah.
other highlights from the report.
So the other side of it then was, that was sort of some of the takeaways sort of from the enterprises. So obviously what we wanted to do was then to go and independently benchmark what actually is achievable across 5G networks today that are using either a public edge or going out to one of the regional clouds. So the test setups was following. We tested across three cities in the US, and also Tokyo in Japan. We're going to be doing London now at the moment, and we'll add that as addendum to the report. But the goal here was, on the left-hand side, there is to run suites of tests from commercial devices, which are hosting Spirent's test software, out to through a 5G network, out to the either edge or cloud locations, which are hosting, again, a Spirent end server, to test various different types of low latency type or latency oriented applications. And this was done as both drive, static, and walk testing in the various locations. So the first takeaway, if we just look at the public cloud as a starting point, so this is no edges involved in this. So we're going through the 5G networks in these locations, and you can see on the left-hand side there for initially for downlink or download latency, we were seeing sort of a ranges between 16 to 27 milliseconds today just by using the public cloud. So on a 5G network. In the US, for example, just using, excluding Tokyo there, that means you could probably, you would need a latency window, or you could guarantee a latency window in these cities of sort of 16 to 25 milliseconds. Now, what was interesting when we looked at upload latency, again, you can see there was a big variation here as well, sort of from 17 up to 49 milliseconds in Tokyo. The best for the US cities would have been 17 to sort of 37 milliseconds of latency. So that's quite good, Tara. For many of those use cases that we're highlighting sort of at the start, you could probably service them on having a low latency. Now, the challenge actually was on the right-hand side here. The actual consistency of that latency varied radically. So you were seeing huge fluctuations in all of the cities between having a latency as low as 17 milliseconds, and then that same city could suddenly fluctuate maybe up to 30 or 40 milliseconds. And what that meant is that because of that lack of consistency, it would be very difficult to actually, for a service provider on the public cloud, to sign up to an SLA where they needed to guarantee that. So primarily probably for a lot of enterprise types of use cases which are mission critical, that would be a challenge. Consumer services you could probably deliver, such as gaming, such as video, because they would be tolerant to that. But for some others, certainly you wouldn't. So then the question became, okay, that's the public cloud. What if the cloud was now hosted at the edge at a city or a zone? Would I get a lower latency and a more consistent latency? And I think the takeaway here is certainly you do get a lower latency. In fact, we saw even in the city of Seattle, latencies as low as 4 milliseconds across the 5G network, going out to having an edge zone in the city location, and uplink as low as 9 milliseconds. So these are really good low latencies, which would meet many of the use cases identified, that the industry wants to serve. But again, on the right-hand side, the challenge was that we also saw variations in consistency in all of the cities. So again, you might be able to achieve 4 milliseconds in Seattle, but actually it might fluctuate up to 9 or 10 milliseconds. Now, what's interesting about that, those fluctuations are not as large as they are to the public cloud. So what that means is that the edge certainly, not only does it provide a lower latency, it can guarantee more consistency within the latency. Now, of course, the challenge is that consistency good enough to give you a window which a customer would be, you'd be willing to sign up to an SLA. So if we just look at them side by side, I think that's the key sort of maybe takeaway in the report. Certainly the MEC latency certainly absolutely outperforms public cloud. The MEC latency is also provides in some cities low enough latencies to meet most of those use cases. But the challenge is you do have various fluctuations across different cities. So for the US, for example, I would have to, if I was going to do an SLA, I couldn't just do it at a per city level. I would need to do it nationally. And that means I would have to probably pick my worst performing city to be the SLA sort of boundaries, because I couldn't guarantee it if an application developer needed it across a national market. I think the other interesting takeaway we did see was that where you see inconsistency, and I've highlighted New York and Tokyo here as the two examples, where both the edge and the cloud latencies were both not very good. In New York, it was on the uplink, and Tokyo was the downlink. This actually highlights it's not actually the cloud at fault. This is actually issues with the actual 5G network. It's the RAN and the core are providing actually impacts onto the latency. And that actually means or identifies in this cases in New York and in Tokyo, the service provider should look to actually optimize their 5G network. It needs better optimized in terms of its internal routing and probably its radio optimization to get its latency down. It was not a fault of the cloud itself or the edge. And that's another key takeaway, is that it's not all down to just simply putting the edge or the cloud or using it. There's still a lot of effort going to have to be done to optimize and tune the 5G network to make sure it's consistent in delivering latency across it. So what
Yep.
that looked like, Tara, for in terms of the, as I said, just as that summary, we just went again and mapped sort of across those use cases that we showed at the start. So if we look at those cities, what use cases could be delivered today with the latency we're seeing? And you can see that many of the use cases are highlighted with the blue dots on them could theoretically be delivered and monetized today by customers. The challenge is for those use cases in these, say, for example, in say transport and logistics, where you've got time critical sensing, although it could be delivered, you might not be able to deliver it consistently. And that's going to be the challenge. So I think the next piece of work service providers are going to have to look at is, it's not just about, as I said, delivering low latency, it's how would they guarantee the consistency of that to be comfortable to sign up to an SLA. Because a challenge between you and I as a human and a machine is that we can tolerate the fluctuations or the inconsistency to a higher degree, where the machine needs it to be deterministic. So that's a little bit of the work that's going to have to go in the future. So the conclusions in the report really are these four key areas that sort of it's highlighted. First of all, the demand side certainly its focus is on reliability and consistency, not just low latency. I think that's the primary takeaway. They would pay for an SLA. They need low latency, but they need it reliable and consistent.
Yeah.
The other takeaway is the variations across regions. If somewhere like in the US, if different cities don't provide a similar sort of consistency of latency, if you're going to roll it out, if you're going to sign up to a national oriented SLA, then unfortunately you would have to sign up to the worst performing city. It's the only way you could guarantee that at the moment. Back to the question you asked me, there is definitely a disconnect in terms of understanding between the supply and the demand side in the industry. I think enterprises clearly overestimate or actually lack understanding what real latency their applications truly need. So they need a little bit of help in probably figuring out exactly what latency and what tolerances their applications can really cope with. And I think there's also a misalignment in their understanding of the 3GPP standards. As I said, they look online, they see it, they think 10 milliseconds or lower is available today, and the reality is, the networks are still a long way away from that. So I think there's an educational alignment needs to be done. In terms of the short-term opportunities, I think consumer services is an absolute no-brainer in reality. Most service providers should look at utilizing edge or even public cloud to offer gaming, video, even augmented reality. I think that can be delivered today. I think if they move towards the more enterprise mission critical services, which are going to need those tightly bounded, consistent SLAs, then that's something that'll probably have to wait for a few more years until they either optimize the networks and get release 16, 17 available. The other takeaway, though, sorry.
Sorry. I just wanted to ask this. As you're discussing these points, like if we happen to have that the expected latencies, the below than 50 milliseconds, right? Say this SLA guaranteed latencies available as we speak. So which industries or which use cases do you think will be some of the first ones to take place? Which are the type of clients who will be willing to sign into this service immediately? Like who's really hungry for this?
Yeah, so I think on the enterprise side, we're seeing there's probably the most advanced industry from that we discussed was around the energy supply. So the utility companies certainly see that. High definition video delivery is probably one of the key use cases they're looking at the moment. And this is to do for process monitoring and security surveillance types of services that they're looking at. There is also a number of use cases in a lot of the factories around partial automation, not full automation, but partial automation of guided vehicles within the factory. Seem to be the very early sort of use cases in the enterprise space at the moment. And what's interesting, most of those as I said, don't require the ultra low latency at this stage. But what they do require is a level of consistency. And in the high definition video case, they also need it on the uplink. So it's the asymmetry. If the latency is actually if they could guarantee that asymmetry, they would sign up to that, because in that case they're pushing large volumes of data back uplink through the network to allow AI to make intelligent decisions and monitoring or maintenance activities.
Okay, and I see that the report talks about the premiums that SLA guaranteed latency contracts can fetch. Any idea of the kind of premiums we are looking at above, the rates that we might have today?
Yeah, we didn't really get enough details on exactly what they would be willing to pay. They kept that pretty secret. Other than they would be willing to certainly pay more. So I can't give you a number. They wouldn't share that.
Okay, but at the mention of a premium, you see that there's positive response, and the enterprise customers feel that it is worth the SLA that they are going to get.
It's definitely seemed from the interviews, it's certainly seemed that large percentage. And that was because they told us in many cases, a lot of them had said that they had tried out other technologies. Initially, many tried 4G and it didn't succeed for them. They had looked at utilizing satellite technologies in some of their remote locations. That hadn't worked for them. And they believe that 5G would actually deliver on this, and it would be more cost efficient than having to roll out a fixed wireline infrastructure deployment. So that seemed to be, I think they seem reasonably comfortable or confident that it is. I think the takeaway is that I think the one standard concern of all of them is just that they think 5G is still an infant technology. So that's a little bit of it.
So I guess this will be a great incentive for operators, to, apart from enhancing the MEC capabilities, perhaps also upgrade to 5G standalone, because I think the report mentioned how, the migration to 5G standalone can significantly, lower down the latencies.
Yes, so just on the recommendations, in fact, it was by 20% we saw. So we did some additional independent testing on a network which has done an early upgrade to standalone, and we were just saying that comparing non-standalone to standalone, we saw a 20% reduction in latency where they'd done the upgrades. So I think that's a pretty positive takeaway as well. If you're going to optimize the network, moving to standalone faster is certainly going to offer, or looks like at this stage is going to offer, huge benefits in terms of reduced latency because of the optimal way it's processing both signaling and user plane data in the architecture, and also it's avoiding the complexities of the current sort of handovers, which are happening quite a lot between setting up a non-standalone data bearer, moving from 4G onto 5G all of the time. So we think that's certainly going to be a huge benefit. I think the other takeaway, Tara, which is interesting, is that by looking again at those results, some of our service provider customers had initially thought they were maybe going to need quite a large number of edge locations. And actually, I think the takeaway here is, by partnering with the public cloud and having those public edge locations, in a few cities, is probably going to be good enough for many of the use cases outside maybe enterprises who will want to have maybe a private implementation. And that means they maybe won't need as much footprint as edge as they initially thought. And that's, I think, is something that again is a good opportunity for early partnerships with the cloud providers to actually probably provide some of those services. I think just the last one I would say, and I just highlighted, was something we did note. Obviously, we're testing to our own end applications. We did do a number of we have looked at testing just to commercial apps that are being hosted out in the cloud. Applications themselves cause latency, and that means if it's a poorly designed end application, no matter how good the network is, no matter how good the cloud or the edge is, if the application is badly designed, it will add an increase to the latency. And that means there's a couple of things here. One, the industry needs to better educate, I would think, the app developer community to make sure they design their apps for low latency if they're going to be deployed on a 5G and on a cloud edge distributed networks. And also there's going to be requirement for visibility in terms of accountability. If there are latency SLAs not being met, where does responsibility lie? Was it in the application, or was it in the cloud, or was it in the network? So having an ability to be able to demark where that their latency impact is going to probably be critical, to make sure that service providers themselves will be comfortable themselves in offering the SLA, that they're able to understand that it is their issue or it's not their issue.
That's interesting because, yeah, I mean, there's a lot of discussion whether the network operators and the cloud providers can bring about the desired latency, but we discussed very little about the application itself. So I think, yeah, you highlighted a very interesting point there. So we see that, when I was looking at the report notes, that there's a mention of the private MEC, right? So what are some of the trends in this space, and what's going to push the private MEC deployments?
Yeah, so now the private MEC, we didn't explicitly test it in the report, although we have done some testing already on that. So obviously the private MEC is interesting because you do get, number one, from a technical side, you do get reduced latency and consistency when it is deployed privately, and that's primarily due just to proximity. It's deployed very, very close. It's on-prem. There's a smaller air interface. There's a very small transport infrastructure connecting to it. So it means you actually, you make it a more lower latent, consistent environment. So you get that benefit. I would say the driver we're seeing at the moment is more to do with a mixture of localized processing and data privacy. Is where most of the enterprises we're discussing with at the moment are asking for the private MEC. So there's a number of their applications. It doesn't probably make a huge amount of sense to maybe backhaul out to a city location or even out to a region to do that type of processing. It would be sensible to do it on site. And similarly also for just maintaining certain data assets on site, from a privacy point of view, rather than having them again going out possibly to the full public cloud environment. So what we're tend to seeing at the moment is this request for, I would call it the hybrid cloud environment, where you have a private edge and potentially breakout going to the public edge, or even right out to the public cloud itself. So it gives them the best of all worlds in that requirement. And I think that's what we're starting to see with a number of the major service providers, where they're looking to offer these sort of three types of capabilities, where you could have a private sort of network implementation with a private edge, and you could have also optional breakout going to a public edge deployment in a city, as an additional sort of use case, depending if that's what you required.
Mm-hmm. Mm-hmm. Well, this points very clearly to testing capabilities as being at the center of enabling this sort of SLA guaranteed latency contracts. So do we have that sort of testing capabilities, and can we sort of, like what you said, determine if the latencies that we have today comes from a network that has been really optimized, or maybe from the application, or can we see where the gaps are?
Yeah, yes. So this was part of the as I mentioned at the beginning. Although this study is just an independent benchmarking, we have our testing solutions deployed within a number of service providers today who are specifically doing this. And we use a technology called active testing, Tara, where we are synthetically injecting traffic into the network at various points, both outside the network on a device, inside the network, and then actually in the cloud itself. And this allows us to synthetically generate various use cases. So, we're making a video call, a data session, etc. And it also allows us to create that segmentation, demarcation of which part of the network is causing the latency impact. And that gives then the transparency and visibility of where the issue is. It's done proactively because we're not waiting for real traffic to do it. We are the traffic ourselves. And it also then identifies what potentially is impacting the latency. So that then helps the service providers, or even the cloud providers themselves, look to potential optimizations. So this is already happening today. We call this continuous monitoring. It's using active testing technology, and it's already deployed in some of the biggest networks in the US. Who've started to implement this with their 5G and their edge deployments, so that they can not only, I would say, guarantee the SLAs and demark where the issues are, but also so that they can guarantee their marketing statements. So we get asked a lot of times also, they want to use this information, these active tests, to demonstrate for their legal requirements that they can market that they've got the lowest latency service for and guarantees.
Okay, great. I think that's going to be a really comprehensive report, and I must say that when we first looked at the title, it's a very interesting title. In fact, the latency expectations versus reality, and I think you touched a lot of good points here and explained some of the questions that a lot of people might have when they first see the report. So that's been great. Thanks a lot, Steve, for the time.
No problem. As I said, I'll send over these. I'll send the slides over to you so you've got them.
That'll be great. So that's all for our session today. See you guys again in our next session.